Hello and welcome back. We're still studying thermochemistry, and I wanted to look at these phase change diagrams a little bit more and then do another sample problem and go over it to make sure you understand what we're doing. This is a phase change diagram of ice turning into steam. So we see temperature and time. Right here at 1, it's a solid. This is solid ice. Oops. Solid ice. When we get to 0 degrees Celsius, that's the melting point of water. And there's this weird thing that happens here. You see that right here to right here, it's flat. The temperature is not increasing at all, but the time is. And think about it, we're still adding heat to this. So why isn't the temperature going up? Well, if you've ever taken ice and melted it, you probably realize it doesn't all just turn into liquid instantaneously at one point in time. So really what's happening here is we put enough heat into this solid, and the ice is going to get smaller and smaller and smaller until right here it totally turns into liquid. The temperature is not increasing because all the heat we're putting into it is being used to break apart the intermolecular bonds in the solid rather than actually heat the substance. So when we get here, it's now a liquid. And we're adding more heat to it. We're going all the way up. And yet again, right here is the boiling point, 100 degrees. So think about it. It's now boiling. You have your water on the stove that's boiling, and you see some vapor coming off of it. And it's going to continue to do that until all of it boils away. You could keep a pot of water on the stove until it just completely vaporizes. And right here is now a gas. So anytime you look at a chart like this, depending on how many of these flat areas there are, will sort of tell us the phase changes. Since if we have 2 flat areas, we're actually going through 3 phases. If we only had 1 flat area, we're going through 2 phases. Now, like I said, this right here is called the melting point. This right here is called vaporization. But let's think about it for a second. What happens if we go in reverse? What happens if we take a bunch of steam and we cool it down? Well, the chart is going to look exactly the same, but it will be reversed like this. We're starting with gas and we're going down to a solid. And I wanted to show you this just to sort of give you a heads up, because sometimes these might pop up on a quiz or a test and people will get confused because they haven't been exposed to it before. Now, rather than vaporization, this is condensation. And rather than melting, this is freezing. Now, the amount of energy is exactly the same. However, in one, it's endothermic. In this, we're putting energy or heat into it. Whereas in this, we're taking it out of it. And so the terminology is a little bit different. So this point here could either be melting or freezing, depending on what we're looking at, and this could be condensation or vaporization, depending on what we're looking at. And also, this is just water. If it's any other substance, the temperatures here are going to be different because all substances have different melting points and vaporization points. So I hope that helps you understand that a little bit. We've gone over it before, but the more we go over it, the better off we will be. Let's go ahead and do a practice question really fast. Calculate the number of joules given off when 32 grams of steam cools from 110 to minus 40. So this is a question based on this type of phase diagram. We haven't done this before, but it's exactly the same concept. Now, first of all, we have to realize the boiling point of water is 100 degrees and the melting point is 0. Or I could say the condensation point and the freezing point. So what I'm going to have to do is calculate 5 different steps. I have to calculate the amount of heat given off when I go from 110 to 100, then I'm going to have to look at the heat of vaporization at 100 degrees. Then I have to go from 100 to 0. Then I have to look at the melting or freezing point here at 0. Then I have to go from 0 to minus 40. So if I think about this, I have 1, 2, 3, 4, 5 steps, just like we did before. Let's look at this step first. In here, I'm going to use Q equals MCAT. I would also use Q equals MCAT in here, and also in here. Here I'm going to use the heat of vaporization, and here I'm going to use the heat of fusion. Although I understand we're not vaporizing, we're using theoretically the heat of condensation, which is the same thing. So we have 32 grams. Let's go ahead and do this one first. 32 grams. And we need to use the specific heat of water, actually the specific heat of steam. Let's go up to our diagram here. We have the specific heat of water when it is a gas. It's 2.02 joules per gram Celsius. Now, yet again, I want to point out, just because this chart has joules per gram Celsius, and right here it has the heat of fusion and vaporization in kilojoules per mole, doesn't mean that every single chart is going to have exactly the same units. You might find the specific heat of water in a different chart. It might be in kilojoules. You might find the heat of fusion that's not in kilojoules per mole. It might actually be like kilojoules per gram. So you really have to pay attention to the units, because depending on what the units are, you might have to rearrange them a little bit. And this one is 2.02 joules per gram Celsius. 2.02. Now, I write it like this to sort of help us visualize what we're doing here. Gram times Celsius. That's really what that is, 2.02 joules per gram Celsius. Sometimes people write it like 2.02 joules per gram, and that's totally fine. But I think if you look at it this way, it helps you understand why the units cancel out. Now let's look at the heat temperature change, which is 10. Okay. And this is 10 Celsius. So yet again, the Celsius is going to cancel, the grams are going to cancel. I'm going to end up with joules. So if I do this calculation, I'm going to end up with 0.64 kilojoules. I converted it all to kilojoules on my worksheet here, but now I'm realizing that I'm going to have to convert it back to joules, so I don't know why I did that. But that's fine. So we have the first step. Now we got to go to the second step. This is going to be the heat of vaporization. And to do that, all we have to do is Q equals 32 grams times the heat of vaporization. But yet again, we have an issue here. This is in moles, kilojoules per mole, and we have grams. This is 40.7 kilojoules per mole. So remember what I did was I actually converted this into moles. 1 mole. And I know water has a molar mass of 18. And it's 40.7 kilojoules per mole. 40.7 kilojoules for every 1 mole. This is grams, this is grams. Just so we know, the units are going to cancel. And we're going to end up with kilojoules. So if I go ahead and do this math, 32 divided by 18 times 40.7, I'm going to get 72.35 kilojoules. So let's go ahead and put some of this up here so it doesn't get lost. We have 0.64 kilojoules Now we have 72.35 kilojoules. All right. So we're done with this step, we're done with this step. Now we need to go from 100 degrees down to 0. Let's do that. These questions definitely take up a lot of space. So we'll use Q equals MCAT. Q equals the mass, 32, times the specific heat. Now this is a liquid right here. So I need to use 4.18 joules per gram Celsius. Joules per gram Celsius. And then my change in temperature is 100 Celsius. 100 degrees Celsius. All right. So if I go ahead and do the math here, I'm going to end up with 13.37 kilojoules. Yet again, I converted it to kilojoules at the end. All right, we're making some progress. Now I need to use the heat of fusion right here. So I have Q equals 32. Remember, I have to convert it into moles. 1 mole is 18 grams. What's the heat of fusion of water? It's 6.01 kilojoules per mole. Okay, so 32 divided by 18 times 6. Now, yet again, if I do this, I'm going to end up with 10.68 kilojoules. Depending on the units, you may not have to convert into moles. Like I said, I've seen in some problems where it's just joules per gram, then you don't have to do that step, so keep that in mind. Now we need to go from 0 to minus 40. Q equals the mass of water, and right here, it's a solid, 2.06. And I'm not going to put the units in at the moment. And now we're going to have 40. So I have to do 32 times 2.06 times 40. And I'll get 2.63 kilojoules. Then I add all of this up, and in the end I'll get 99.68 kilojoules. And then I can put actually a minus here because I'm actually getting rid of this energy. This heat's coming out of it because it's going from steam and cooling down. So that would be the answer. Now, one other thing I want to point out is I have seen some problems where they simplify this entire process, and rather than using water, they might use some other material and give you the specific heat. I saw a problem where there was a it was a phase change diagram like this, and basically it only said the specific heat of, let's just say, glass is whatever. They gave a specific heat, but they didn't say the specific heat when it's a solid, a liquid, or gas. It was just one specific heat. They did give the heat of fusion. They gave the heat of, vaporization. So how do you do a problem like that when they don't actually give you the 3 different specific heats? And the answer is just do a simplified version, Q equals MCAT, and just do your temperature change right here from here to here. use that one specific heat and just make one calculation for all of this, and then do a calculation for the heat of vaporization and the heat of fusion. So you're only doing 3 calculations and then add it all up. Personally, I dislike that question greatly because it oversimplifies something to the point where I think it brings confusion to it. It actually is possible to make something so simple it doesn't make sense. So that would never happen. There would always have to be different specific heats, but maybe they want to make these questions easier on some high school tests. I'm not entirely sure. So anyway, I hope this helps you understand this a little bit more. This is the last time we're going to look at phase change diagrams like this, the last video, and then we're going to move into some other parts of thermochemistry. So I hope that helps you, and yet again, if you have any questions, let me know.